Okay, so we've covered these first few slides already, but I am just going to recap a few things. So we need to know about certain reactions of acids with different substances, and one of the first substances we have to do is metals. And there's a nice little acronym to help us remember how metals react with acids. That's this MASH that we've got at the top there. All right, so MASH there. And basically a metal and an acid is going to produce a soluble salt and hydrogen. If we just think about the state symbols, if you think about all metals except mercury, if you think about they're all solids, so I'm just going to write the state symbol in there, so S for solid. All acids are aqueous because they're all dissolved in water. If it's a soluble salt, the salt's going to be an ionic compound, but if it's soluble, that means it's dissolved in water, and that's what that's going to be. That's going to be AQ, or aqueous as well. And then hydrogen is a gas, so we're going to have G. So sometimes you can get questions that ask you, what would you observe if this reaction took place? And state symbols are really very useful for that. So we can see we've got a solid on the left-hand side and no solid on the right-hand side. So one of the things that we're going to see is we're going to see the metal disappear. Okay, and then something else that we can see is, again looking at the state symbols, on the right-hand side we have a gas, okay, and there are no gases on the left-hand side. So the other thing that we'll see during the reaction is that we'll see bubbles or fizzing or effervescence, and that's because of the hydrogen gas that's produced. So there are three main acids that we have to be aware of. I mean, there are many acids, and we're going to come across more than just the three, but the three really common ones that feature in our course are hydrochloric acid. That's the first one that we're going to look at. And you'll notice that whenever we use a metal and we react it with a hydrochloric acid, we are always going to get a chloride. Okay, so if you see that a product is a chloride, then you know that the acid that was used to make that salt had to have been hydrochloric acid. Similarly, sulfuric acid gives a very specific salt as well. So if we're using sulfuric acid, we're always going to get a sulfate. Okay, so they always make sulfate salts. So if you've got sulfuric acid, you're going to make sulfate. And then the third principal acid that we're going to consider is nitric acid. And again, if we use nitric acid with a metal, our salt is always going to be a nitrate. Okay, so hydrochloric acid produces chlorides, sulfuric acid produces sulfates, and nitric acid produces nitrates. So if you haven't done this already, and I know a number of you have, but some of you did miss the lessons, in your reactions of acids booklet, which you either already have or which you can download from my classroom post, I want you to find the sheet. Unfortunately, it's not quite in the right place. There's a sheet that says acids reacting with metals, and the first question or first sort of thing that they want you to do is to give the generic word equation for the reaction between an acid and a metal, and what that means is you need to give that MASH equation, okay? And I will post the answers in a short while. Now, if I write the formula, well, you've got the formula here of hydrochloric acid, sulfuric acid, and nitric acid, and I'm just going to add a couple more. So one of the ones I'm going to add is phosphoric acid. So phosphoric acid is H3PO4. One of the things that you'll notice is a common feature of all of these acids that we've got here is they all contain hydrogen, all right? All of them. And it's not the hydrogen per se that makes something an acid. It's that when these substances dissolve in water, it says here that they fully ionize, and I'll just explain what that means in a second, but they fully ionize and they make or release H plus ions, and it's the H plus ions that are what are making something an acid. And if you think about how we measure the strength of acids, and that is using the pH scale, that H there, it represents hydrogen, okay? So really what we're measuring is the hydrogen ions, okay? Okay, we're measuring how many hydrogen ions. That's essentially what the pH scale does, but we will look at that a little bit more. So this fully ionized bit, what does it really mean? So notice that we're saying when they're dissolved in water. So let's say we've got hydrogen chloride, and hydrogen chloride is a simple molecule. It's just a covalent bond between the hydrogen and the chlorine, and it's a gas. If we were to bubble it through water, so I'm going to just put an AQ above the arrow, so that just means what it means is actually I'm dissolving the hydrogen chloride in water. What will happen is that covalent bond between the hydrogen and the chlorine will break, and it will break in such a way that both of the electrons in that covalent bond, because remember a covalent bond is a shared pair of electrons, both of them will go with the chlorine atom, and that will make a chloride ion, okay, because it has all of the electrons around its outer shell, has one extra electron in essence compared to its protons, and what was the hydrogen's electron has gone with the chloride, or the chlorine, sorry, to make chloride, and we get a H plus ion. So when they say fully ionize, what they're saying is that the molecule where the hydrogen is bonded to something else, that bond is breaking, and we're getting two separate ions, and one of those ions is an H plus ion, and it's the H plus ion that is making something an acid. So the next bit is building on the previous work we've done on the reactivity series. So the first thing is, if you remember back when we were doing the reactivity series before, we did have carbon there on the reactivity series, and it was there to help us decide if we could displace a metal from oxygen, or the metal from its oxide, so that we could just get the metal, so whether the carbon displaced it or not. It was a redox reaction, if you remember, as well there. So redox, we'll talk about redox a little bit more in a second. But you'll also notice on the reactivity series is hydrogen. Okay, and when they're writing hydrogen here, they're really talking about a hydrogen in the sense of H plus ions, in the sense of an acid. So if we're reacting a metal with an acid, we're still going to consider the reactivity series. So hydrogen from an acid is on the reactivity series, and if we're reacting a metal with an acid, if the metal's more reactive, one of the things it can do is it can reduce the H plus ions in the solution. So we've got to just remind ourselves about those H plus ions. But anyway, with looking here, we've got a reaction between magnesium and hydrochloric acid. So here's magnesium, and if we look on the reactivity series, there it is there. And then the other thing that we're reacting it with is hydrogen. And the hydrogen on the reactivity series is we can see is below magnesium. So magnesium is higher on the reactivity series, and so that's able to reduce the hydrogen ions. So just to make that a little bit clearer, if we look at our HCl, and if we look at that HCl, we know that what it really means is H plus ions and Cl minus ions. That's the reality, okay, in the actual solution. So our H plus ions have a charge of 1 plus, or plus 1. And if we consider hydrogen on the right hand side, everything that's an element, or anything that's an element, so it's simply its chemical formula as an element, has a charge of 0. So we are going from plus 1, okay, to 0. So that is reduction, okay, because that is the gain of an electron, or gain of electrons, I should say, because each H plus is going to gain 1 electron, but we've got 2 of them to form H2. So we get hydrogen gas as a product. The metal is also changing its charge. So we look at magnesium on the left, it's an element, so it has a charge of 0. And if we think about magnesium on the right, well, magnesium is in group 2. So we know if it loses its electrons to get a full outer shell, which is what happens when an ionic compound is formed, and it's in group 2, we know its charge will be plus 2. So we know that we have got oxidation going on here. All right, so we've got loss of electrons. Okay, so what that means is that overall These acid-metal reactions that we're looking at, they are examples of redox reactions. Remember, redox is when a reaction involves both reduction and oxidation at the same time, and really you can't have one without the other anyway. So if we just look at that again in a different reaction, so hydrochloric acid plus zinc, and again if we look back at our reactivity series, we'd see that zinc is higher than hydrogen on the reactivity series, so this reaction will take place. The hydrogen in our hydrochloric acid has a charge of +1 because it's H+. We know that hydrogen gas as an element has a charge of 0, so that we can see that there is, well, each hydrogen ion is going to be gaining 1 electron, so each hydrogen ion must gain 1 electron. We call that reduction. So if we're trying to represent that as a half equation, you know that we're making hydrogen, and you know that we started with H+ ions because that's from the acid. We've got to balance have a balance equation. So we've got 2 hydrogens on the right and 1 on the left, so it's going to be 2 H+ ions. That's how we're balancing the hydrogens. But the other thing that we have to balance is charge. And at the moment on the left-hand side we've got 2 1+ ions, so that's +2. On the right-hand side we've got the element, so that's 0. The only thing that we can do is add electrons, and electrons bring numbers down. So we would need to add 2 electrons to bring the left-hand side's overall charge down to 0 so that it matched the right-hand sides. So here we're looking at it from the perspective of zinc. So zinc is an element on the left-hand side, right? It's just the metal, so it's going to have an overall charge of 0. Zinc on the right-hand side, well, it's not in a group, it's in the transition metals. I'm afraid it's one of the metals, one of those ions that you just are going to have to remember. It's one of the ones you're going to have to learn, but it has a +2 charge. So we can see that what's actually happening here is that zinc is losing 2 electrons. So again, if we're going to write the half equation, we've got zinc metal on the left-hand side. We have got zinc ion on the right-hand side, and we have to make sure that the charge is balanced as well as the numbers of each element. Well, we've got 1 zinc on both sides, so that's fine. The only thing we can do, we've got 0 on the left-hand side, overall charge, +2 on the right. The only thing we can do is add electrons, because this is all about electrons. All they can do is bring the number down. We need to bring it down from +2 to 0, so we have to add 2 electrons. And that's oxidation. So again, in your booklet that you've got, I'd like you to please, if you haven't already, to do these worksheets, and I'll make sure that you get the answers. But obviously, if you have any queries, just get in touch and I'll try and sort them out. So some of you got to do an actual acid metal, sort of like a mini practical. So you reacted magnesium with hydrochloric acid, you reacted zinc with hydrochloric acid, and you added copper to hydrochloric acid. And one of the things that you noticed was that the fizzing was vigorous. There was a lot of fizzing when magnesium was added. When the zinc was added, there was some fizzing, but not. It wasn't as vigorous as that with magnesium. And then when you added copper, nothing happened at all. And again, if you go back to the reactivity series, you'll see that copper is below hydrogen on the reactivity series. So all of those metals below hydrogen on the reactivity series will not react with acids. So all of the precious metals, gold, silver, platinum, but also if you think of copper as a sort of ornamental metal, even though we use it for many other things, that doesn't react with an acid either. The other thing to say is, if it was hydrogen gas that was being given off, if we were able to collect the gas, and we could do that by holding our finger over the test tube or putting a bung in there, as long as we were able to collect enough of it, one of the things that we could then do is test it by inserting a lit splint, so basically a flame, and we would get a squeaky pop if hydrogen was present. Okay, so I just want you to have a look at what you've got in front of you here, and have a think about, just sort of almost talk through in your head what you think is happening, and it's going to be something that we look at a little bit more closely in a short while. But essentially, this is one of the core practicals that we need to do for our GCSE. So if you can just try and think about what you think the storyboard is telling you, what the steps were that are taking place, and then we'll talk about it some more in a bit. Okay, so neutralisation is something that you're familiar with from doing acids and alkalis in year 7. And neutralisation is a type of reaction that you get if you mix an acid and a base. And so this is a new word for us, base. Okay, we'll come to that in a second. But if you react an acid and a base in the correct proportions, you get neutralisation, and that what you get, the resulting solution that you get, should have, if you've done it properly, a pH of 7. Okay, so the acid is being neutralised. Now, a base is anything, any substance that is able to neutralise acids. Okay, so a base is anything that can neutralise acids, and we can basically classify bases in two forms. We can think of them either as being soluble in water, in which case we call them alkalis. So those are the ones that you're familiar with already, the ones that you did in year 7. They would have been in bottles. They are solutions. But you can also get insoluble bases. So insoluble bases will not dissolve in water, but they will neutralise acids. So how can we tell quickly if something is a soluble base, an alkali, or an insoluble base? That's really going to be the second part of the substance name. So if you look at the ones on the left, if you look at what we're looking at here, which is alkalis, and there we've got a list of example alkalis. So we've got sodium hydroxide, lithium hydroxide, potassium hydroxide, calcium hydroxide, magnesium hydroxide. So something that is common to all of them is that they are hydroxides, and that is a particular ion, OH minus. Again, it's one of those ones that you have to learn. And so it has a 1 minus charge, and essentially if you're looking at a substance and it has hydroxide in its name, or it has OH in its formula, then you are looking at an alkali. If we think about insoluble bases, there are really two types that we need to be familiar with. So that's any metal oxide. So we've got here calcium oxide, magnesium oxide, copper oxide, sodium oxide. And then the other ones that we have to be aware of are carbonates. So calcium carbonate, magnesium carbonate, and sodium carbonate. So typically, metal oxides and metal carbonates are insoluble bases. I use the word typically because some of these are in fact soluble, but I think at GCSE this isn't really going to be an issue. So I just want you to have a look at the list on the left-hand side, potassium hydroxide, calcium oxide, etc. And I want you to just have a think and jot down whether you think they are an alkali or whether you think they are an insoluble base based on what we've just had on the previous slide. So I'll just give you, why don't you pause the video, have a think about that, jot down your answers, and then I'll give you the answers. Okay. So potassium hydroxide is an alkali, calcium oxide is an insoluble base, copper oxide is an insoluble base, sodium hydroxide is an alkali, lithium hydroxide is an alkali, calcium hydroxide is an alkali, calcium carbonate is an insoluble base, and magnesium hydroxide is an alkali. In truth, magnesium hydroxide isn't terribly soluble in water, although it is a little bit. So it's a little bit dodgy, that one. But again, for the purposes of our GCSE, I think it's safest to feel that hydroxides are alkalis and metal oxides and metal carbonates are insoluble bases. So we're going to look a little bit more closely at the reactions between metal oxides and acids. So remember, metal oxides are insoluble bases. Even though they're insoluble, that just means they won't dissolve in water. That doesn't mean they won't react with acid. They do react with acid, and they do form a soluble salt. So if we just look again, we've got the equation underneath, an example one of calcium oxide and hydrochloric acid reacting together, and they're going to make calcium chloride and water. Let's just look at the state symbols because they've given them to us, and we should always pay attention to state symbols whenever they're given to us. So the calcium oxide is a solid, We've got a solid on the left-hand side, and we don't have any solid on the right-hand side. So what's going to appear to happen is it's going to appear to dissolve. It's not actually dissolving, it's reacting, but that's what it's going to look like. And that will continue to happen. It will appear to dissolve for as long as it's reacting with an acid. So if we want to make sure that we have neutralized all the acid, we simply have to keep adding the calcium oxide or the metal oxide until the metal oxide stops appearing to dissolve, because that will mean that the acid has all been used up, and that will explain why the calcium oxide no longer appears to dissolve, because it's now just in a soluble salt and water, and it's an insoluble base. It was only appearing to dissolve because it was reacting with the acid. So once we've used up all of the acid, any additional insoluble base that we add will remain as a solid. Okay. These are just a couple of different metal oxide and the same metal oxide, calcium oxide, but we're reacting it with 3 different acids: hydrochloric acid, sulfuric acid, and nitric acid. The only difference is the name of the soluble salt. Because we use hydrochloric acid in the first, we get a chloride. Because we use sulfuric acid in the second, we get a sulfate. And because we use nitric acid in the third, we get a nitrate. But if you look at them, they're all metal oxide plus acid produces a soluble salt and water in every case. And because we've made it calcium oxide each time, it's always the soluble salt always has calcium at the beginning of its name. Okay, so now we're just going to look at the metal carbonate and an acid reaction. So exactly as we get with metal oxide, we get a soluble salt, and exactly as we get with a metal oxide and acid, we get water. But there's one other product. If we're using a carbonate, we're also going to get carbon dioxide produced, and that's going to change the appearance of what's happening during the reaction. So let's still focus on the insoluble base for the moment. We can see from the example equation of calcium carbonate and hydrochloric acid, they've given us the state symbols, and we can see that the carbonate is a solid, and so we have a solid on the left-hand side of the equation. And if you look at the right-hand side, aqueous, liquid, and gas, we don't have any solid on the right-hand side. So again, just as before, the calcium carbonate is going to appear to dissolve. It's not dissolving; it's reacting with the acid. But we also need to look at the right-hand side of the equation, and we can see in the carbon dioxide that's produced, that has a state symbol that tells us it's a gas. I mean, we could probably work that out anyway ourselves. There's no gas on the left. There's a gas being produced in the reaction. So what we're also going to see in this reaction is effervescence. We're going to see bubbling. We're going to see fizzing as the carbon dioxide is produced. So I'd like you now to have a go at this worksheet, which is in your booklet. So the neutralisation of acids with insoluble bases. So it's based on what we've just been covering in the last few slides. If you have any queries, get in touch with me. Okay, so this is the core practical that we're going to need to do. It's based on the metal oxide and acid reactions that we've just been looking at. So we're measuring, in number 1, we're measuring a specific volume of, in this case, sulfuric acid. We're going to be adding copper oxide. Copper oxide is a black powder. And so we add the copper oxide to the sulfuric acid, and we heat the mixture gently. That's what part 3 is showing. Whilst we're heating it gently, we're going to be stirring the reactants so that they get an opportunity to react with each other, and we're going to keep adding a little bit of copper oxide at a time, and we're going to keep doing that until no more copper oxide appears to dissolve, because we know at that point all of the acid must have reacted, and that's really what we want to do. We want to make sure that all of the acid has reacted, so we're going to be adding the copper oxide until it is in excess, until we've added too much of it. Because we've added too much of the copper oxide, we're actually going to have little black bits in our solution. So that's why in part 4 we have to filter our mixture. So that's going to allow the filtrate, which is a blue solution, to pass through the filter paper, and that's going to be copper sulfate solution. And any of the copper oxide that was unreacted is going to be kept behind on the filter paper. So we're filtering, we're removing the solid copper oxide really from the mixture. Then we're going to pour our filtrate or copper sulfate solution into an evaporating basin. That's what number 5 is. And then we are going to put a beaker of water on our Bunsen burner and have the evaporating dish on top of that beaker of water. The reason for that is our water will boil at a temperature of 100 degrees Celsius, and then we're basically producing a water bath. Our beaker of water, boiling beaker of water, is going to warm the evaporating dish, and we are going to essentially evaporate some of the water in our evaporating basin in our copper sulfate solution, and we'll basically be heating it until it becomes a saturated solution in the evaporating basin. And the way that we can tell it's a saturated solution is that just on the edge of where the edge of the solution in the evaporating basin, once we begin to see little crystals around that very edge, that's when we have a saturated solution. A saturated solution is when no more solute can dissolve in the solvent. So if we are evaporating off the solvent, we are making it more and more concentrated, and at one point it becomes saturated, and that's why we get the little crystals forming around the edge, because they cannot stay dissolved. Once that's happened, once we get that little ring of crystals around the edge of the solution, we take it off the heat, and then we put it, say, on our windowsill or somewhere, and we allow the remaining water to evaporate slowly. And if it evaporates slowly, what we'll get is these lovely crystals that are shown in part 7 of this picture. So I'm going to also attach a link to this practical to the classroom post. It would be great if you could watch the video on the practical. And obviously when we're back in school, whenever we're back in school, we'll be doing that practical, but you'll already have a very good understanding, hopefully, of what's actually going on. So here are just some instructions that take you through. I think your booklet is missing the exact statements. So if you could add those to your booklet, that would be great. If you need to just pause the video to be able to do that, please do. Okay, so we're now going to consider alkalis. And again, this is about us appreciating formulae, appreciating how we determine formulae. Honestly, guys, you will make your lives so much easier in chemistry if you learn how to determine the charge of an ion that is in a group on the periodic table, and also if you just remember those polyatomic ions that you've got on a list, things like sulfate, ions that have more than one atom. If you just learn their formulae and learn their charge, it will make your life so much easier. So if you look at all of these chemicals that we've got in front of us, got calcium chloride, magnesium sulfate, magnesium nitrate, sodium sulfate, copper 2 sulfate, and copper 2 chloride. They are all ionic compounds. They are all a metal and a non-metal. So we are looking at charges here, okay? I know it says at the top anyway, use the formulae of common ions to write formulae of these salts, but let's just sort of understand how we could have known it was ions in the first place. So calcium is in group 2. So when it forms an ion, it's going to be a 2+ ion, okay? So we've got calcium 2+. Chlorine is in group 7. So when it forms an ion, it's going to be 1-, okay? Magnesium is in group 2, so when it forms an ion, it's going to be Mg2+, and sulfate is one of the ones that you just have to learn. So the formula of sulfate is SO4, and the charge is 2-, okay? Magnesium nitrate, well, we've already said about magnesium, group 2 metal, so 2+, and nitrate, another one of those ones you've got to know the formula and charge of, so it's NO3 and with a 1- charge. Sodium, group 1, so it's going to have a 1+ charge. Sulfate, again, one of the what we've already said, the one that you need to learn, SO4 and 2- charge. Copper 2, so that Roman numeral 2 is telling you the charge on copper. So copper is not in a group, it's in the transition metal block. It's the Roman numeral that tells us the charge. And then sulfate again we've already done. And then copper 2 chloride, well again copper 2, so it's copper 2 plus. And then the chloride, remember chlorine is in group 7, so the ion will become a 1 minus ion. So the charges have to cancel out when we write the formulae, so we have to write the right number of each charge so that they cancel each other out. We've done that many times. If you're still stuck on that, please get in touch with me and I'll talk to you about it separately. But I would like you now to just pause the video and for you to try and work out the formulae of these different substances. Okay, so we need 2 chloride ions for every 1 calcium ion to have an overall charge of 0. We need 1 magnesium for every 1 sulfate for an overall charge of 0. We need 2 nitrates for every 1 magnesium for an overall charge of 0. And just notice, because we need 2 NO3s, we've got the NO3 in a bracket and a subscript 2 outside. We need 2 sodium ions for every 1 sulfate ion to have an overall charge of 0. It's a 1-to-1 ratio of copper and sulfate in our copper 2 sulfate, sorry. And we need 2 chloride ions, 2 1 minus ions to cancel out the 2 plus copper ion in copper chloride, so it's CuCl2. So we're going to look a little bit more closely at alkalis. Remember their solutions because they are bases that are soluble in water. Okay. And also remember that one of the things that, or one of the ways that we recognised whether something was going to be an alkali or not was because it had hydroxide in either the formula or the name. So hydroxide, 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 and so on, right? So you can see that OH, and that is an ion, okay, it's OH minus, okay, so that's also another one of those ones that you have to remember. Now, when we did acids, we recognised that every acid had hydrogen in its formula, and then we also said that when acids dissolved in water, or when substances dissolved in water, an acid was formed if we had, if they were fully ionized, i.e. if they split, and we got H plus ions formed. And there's something similar happening here. So if we take a formula like sodium hydroxide, so that has the formula NaOH, when that, it can actually be a solid, it's an ionic compound. What we've said is they're soluble in water. So if we add them to water, so it is a solid. Now we know it's soluble, so when any ionic compound is dissolved in water, we know that the giant lattice breaks apart and the ions become free and they're totally separate from each other. So if we dissolve our sodium hydroxide solid in water, what we in fact have are Na plus ions dissolved in water, aqueous, and OH minus ions, aqueous. Okay. So it's these OH minus ions that are going to be reacting with the H plus ions. So the neutralisation reaction is going to be between the OH minus ions and the H plus ions. The OH minus ions from the alkali, the H plus ions from the acid. The more OH minus ions that we have, or the higher the concentration of OH minus ions, the higher the pH. So you can see that what we think of as a weak alkali, pH 8, that's a low concentration of hydroxide ions. But if we think of strong alkalis like pH 7, then we're looking at a high concentration of hydroxide ions. So you know from year 7, pH 7, that's neutral. And you also know that anything above pH 7 was alkaline, and anything below pH 7 was acidic. And obviously we can have something that's strongly acidic, has a pH of 0 or 1. We can have something that's weakly acidic, something like a pH of 5 or 6. And similarly with alkaline, it's weakly alkaline with a pH of say 8 or 9, and it's strongly alkaline with a pH say of 13 or 14. Notice that the universal indicator going from acidic to alkaline, it's just like our rainbow. So Roy G. Biv was a way of remembering the colours in a rainbow, and that's a little bit like what we've got here. So red, orange, yellow, green, blue, and okay, and we've got purple instead of indigo, violet, but it's essentially the same order as the rainbow. So if you can now please do the worksheet on alkalis. which again is in your booklet, and I will post the answers at some point shortly. And if you have any problems, please just get in touch. So just a brief recap of acids. All of the acids have hydrogen in them. What then makes them an acid is the fact that those hydrogens the bonds that they have will break, producing H plus ions. And so really the pH is a measure of the concentration of H plus ions. So that H in pH is representing hydrogen or hydrogen ions. We sort of discussed this already. Anything with a pH less than 7 is considered an acid, and it's the presence of H plus ions. Let's just cross that out. Hydrogen ions or H plus ions in a solution that makes it acidic. And again, the lower the pH, the more acidic something is. And again, we've basically discussed this. We can use universal indicator paper or universal indicator solution to add. We can add it to a substance that is a solution already, and find out whether it's something that's acidic or neutral or alkaline. So when we react an acid and an alkali together, we can get neutralisation. If we react them in the right proportions, then we're going to get a soluble salt and water, and the combination of those two will have a pH of 7, and we can confirm that's the case by adding universal indicator, which would turn green. So an acid and an alkali react together to form a soluble salt and water. Here's a classic example: hydrochloric acid and sodium hydroxide reacting together to form sodium chloride and water. So let's think about this a little bit more carefully then. We know that something is an acid because it has H plus ions, and we know that something is an alkali if it has OH minus ions, and we know that something is one thing that we know is neutral is water. And if you look at what I've written there, hopefully you're starting to see a connection or relationship between them. So there is something called a neutralisation ionic equation. Okay, so if it's an ionic equation, it's got to involve ions. So we are reacting H plus ions with OH minus ions, and we are getting as a product water. So that's what's happening in every acid and alkali reaction. It's H plus ions reacting with OH minus ions, making water. So now if you could please do the worksheets on acids and neutralisation. Again, some of the slides that we've just done really should be covering this. But again, if you have any problems, please get in touch. Okay, so now we're considering the fact that not all acids are equal. They can actually be classed as either strong or weak. There is an absolute difference between them. So all of the acids we've considered so far, hydrochloric acid, nitric acid, sulfuric acid, they're all going to be considered strong acids. You're aware of many other acids. In fact, you come into contact with many, perhaps on a daily basis. So vinegar is one. It contains a substance called ethanoic acid. But also citric acid. Every time you're eating fruit, in many fruit juices, in all sorts of things, actually citric acid appears. And we don't have any problem with that. So it isn't always the case that an acid is going to cause harm or cause a burn. Although, if you think about maybe getting lemon juice, which contains citric acid, in your eye, that can actually sting a little bit. So we need to look at this difference between strong and weak a little bit more carefully now. So when we were considering acids right at the beginning, and we realised that what made an acid was the presence of hydrogen, which then became H plus ions, we were talking about those substances that we were looking at, like hydrochloric acid, as fully ionizing. So what that meant was that every molecule of HCl became H plus and Cl minus when it dissolved in water. And that's what I've just tried to represent. So any of the hydrogen chloride gas that we dissolved in this water, all of it would have fully ionized into H plus ions and Cl minus ions, and that would give us a low pH. We'd end up with something with a pH of around 0, 1 or 2, depending on the concentration. So we're going to compare equal concentrations of hydrochloric acid and ethanoic acid, vinegar. Let me just write the formula of ethanoic acid for you so you can understand perhaps a little bit better what we're talking about here. So ethanoic acid has the formula CH3COOH, and when there's an ionization in this molecule, the hydrogen that's going to come off, the hydrogen that's going to make or become H plus, is the one in between the O and, well, is the one next to the O. All right, so we only get partial ionization in a weak acid, or that's how we're terming it. We're terming it partial ionization. What that really means is that not every molecule fully ionizes. It's a proportion of them. So in reality, if we looked at our weak acid up close, whereas in HCl, every HCl has become H plus and Cl minus, in our weak acid, in our ethanoic acid, that is not the case. It's going to look something more like this. So you can see that most of the ethanoic acid molecules are still as they were. They're still CH3COOH, but we do have a small number of them ionizing, or in my example only one, but of course we're talking about an enormous number of molecules, but we do have some H plus present that wouldn't have been there before, and that's why we have something now that is weakly acidic. Okay, so we've got a strong acids where there's full ionization. We have weak acids where there's partial ionization. So our fully ionized acids are going to have, generally speaking, a much higher concentration of H plus ions. Our weak acids are, generally speaking, going to have a lower concentration, and that's why we get a difference in the pH, because pH is a measure of the concentration of hydrogen ions. So you would have done this practical in school, but and hopefully we will get to do it. But until then, I'm just going to show you what the results would have been if we had tested these different acids with universal indicator, and what that would have told us about whether they were strong or weak acids. So all of them would have been the same concentration, okay? So all of them would have been something like 1 mole per decimeter cubed, and then, but they still would have, some of them would have fully ionized, some of them would have partially ionized. We would have a difference in the concentration of hydrogen ions, which is what we're really measuring with pH, and then we can see what the result of that would be if we used universal indicator paper. Okay, so these are the results. So ethanoic acid, you get something like an orange colour, pH of about 3, possibly 4. It's a weak acid. Nitric, red, pH 1, strong acid. Citric acid, something like 3, weak acid. Carbonic acid is even weaker than citric and ethanoic acid. It would probably give a yellowish colour. pH 4 to 5. And then hydrochloric acid and sulfuric acid, both of which are strong acids. So maybe just pause and take those results down. Okay, so the pH scale goes from 0 to 14. It's a logarithmic scale. Now, those of you that do geography, you probably or hopefully have done the Richter scale. So you've done the strength of earthquakes using something like called the Richter scale. So you can have an earthquake with a value of 5, or an earthquake with a value of 6 on the Richter scale, and the difference between that 5 and 6 would be 10 times. So an earthquake with a value of 6 on the Richter scale would be 10 times more powerful than an earthquake with a value of 5 on the Richter scale. And it's similar with pH. The difference between a pH of 1 and a pH of 2 is 10 times difference of concentration. So it's a logarithmic scale. So you need to know that the fact that it's called a logarithmic scale, but what you do need to know is that for every 1 pH value increase or decrease, the concentration of hydrogen ions changes by 10. So this gives you can see it's done in standard form here. So pH of 1 has a concentration of 1 times 10 to the minus 1 moles of hydrogen ions per decimeter cubed. And so you can see those numbers. You look at the one on what it's talking about on the right, an acid with a pH of 2 has 10 times fewer H plus ions than an acid with a pH of 1. So there's a difference factor of 10 between every pH value. So I'd like you to just have a go at this task, this pH scale task, and it's the very final sort of activity in the reactions of acids thing that we have to do. And I will send you, or I will post the answers to all of these worksheets that you've been doing through this booklet. But basically, this is based on what you saw on the previous slide. So use the previous slide, go back on the video to try and answer the differences between, say, pH 1 and pH 3. How many times difference is that in terms of hydrogen ions concentration? Okay, well, that's it. I'm just going to finish with what I think is the best joke in chemistry because it's relevant to this topic. So there was a chemistry teacher in the Second World War, and he decided to volunteer, and he got called. He went and joined the army, and they sent him to a camp, and they said to him, right, look, what we want you to do is we want you to be in charge of the radio. Okay, so if anything starts happening to our camp, if the enemy start to attack, you've got to let HQ know. All right, it's really important. That's your job. That's what you got to do. Anyway, weeks went by, nothing happened. And then all of a sudden it kicked off. There was guns, there was mortar, the planes were firing in, they were coming in. And he ran to the radio and he said, right, I've got to let HQ know, I've got to let HQ know. And he sat down and he took a deep breath and he said, okay. This is the army, they like codes. So he got on the radio and he went, NaOH under NaCl, NaOH under NaCl. And the people at HQ said, what are you talking about? He said, base under assault. I'll leave it there. Enjoy. Take care. Bye.